pinned at both ends. Okay, so both ends are pinned. So what do we mean by pin? Is that for this case, if we look at the axis, okay, so I'm going to call this part A, the bottom part A, the top part B. When it's pinned, right, the x motion is equal to 0. Okay, so when it's pinned, the x motion is equal to what? 0. Okay, sorry, it's not the x motion. What I mean, the x motion, the moment is equal to 0 when it's pinned. So when we know that it's pinned, the moment is always equal to 0. So now the thing is this: how will the structure buckle? Okay, so we're going to find, okay, what we're going to do. So we are going to find what is our critical load. Okay, what is our critical load? We want to determine what's our critical load. So from our critical load over here, right, we are going to relate how is P. If P is equal to 16 times 10 to the power 3 Newton, we want to find what is our P critical. Okay, so if P critical, right, is less than or is greater than P, right, means the structure will not buckle. And then from here, we are going to determine the factor of safety. Okay, in fact, the question did ask determine the factor of safety if the structure will not buckle, and the factor of safety is equal to P critical divided by P. Okay, so that's a factor of safety. So now let's see how this structure will buckle. Okay, so how the structure will buckle. So with the structure, the way that so there are two possibilities that the structure will buckle. Okay, so what are the possibility? So one of the possibility, it will buckle on the YZ plane. Okay, so buckling will occur at the YZ plane. Okay, so YZ plane, so I'm going to sketch our YZ plane now. That is our Z, our YZ plane. Okay, so YZ plane, if I look at the structure on the YZ plane, right, so our YZ plane, it will look like this. So YZ plane, so this is our structure, right? So I'll come back to here. So YZ plane, it is this plane. So this is your YZ plane, right? That's your YZ plane. So you are viewing from here now on YZ plane. Okay, so you're viewing from here now, YZ plane. So if we draw that, so it is basically, you can still see this. You can still see this. And then you have a load coming down at 16. Well, 16 times 10 to the power 3. Okay, and then we realize that this is rotation about x-axis. Okay, so how this structure will deform? It will deform in this axis. So that is our neutral axis, right? And the structure will deform this way. Now the structure will deform. Sorry. Then the structure will now deform this way. Okay, so this is how the structure will be formed. So the bending curvature, is about the x-axis. Okay, so when the bending curvature is about the x-axis, we have to use what? We have to use, okay, have to employ IXX, second moment of area. Why is that? Okay, why apply IXX? Okay, remember, we are looking at this like bending, right? So remember, when we have stress in the Z direction, what do? We say that this is equal to my over Iyy multiplied by x plus by mx over Ixx multiplied by y. Because the bending moment over here that we are doing now is about the what? X-axis. That's why you have to employ what? Ixx. Okay. Why are we looking at the second moment of area? Okay. The second moment of area that is smaller is the direction, or is the one that we have to use to calculate the critical load. Okay. Smaller second moment of area means lower resistance to bending, right? So smaller second moment of area means less resistance to bending or buckling. Okay. So now, one of the possibility that it will buckle in the YZ plane. Okay, buckling will occur in the YZ plane. Now, buckling can also occur. So another possibility is buckling, right? Buckling can also occur, right, in the, so the other plane that it will buckle is this plane over here. I'm going to use a different color. It can buckle in this direction also. So this will be our XZ plane. Okay, buckle in the XZ plane. Okay, so now we are going to draw our XZ plane now. Okay, so we are going to sketch our XZ plane. Right, so when we sketch our XZ plane, so XZ plane means that, so at that plane we are I'm going to use a different color. We are looking at our eyes is here, so this is viewing at the XZ plane, where the other one we were viewing in the YZ plane. Right, so now we're going to sketch the structure again. So we're going to sketch the same structure. So you'll see a different thing because the view is different now, right? So at that view, you will just see hidden detail. Okay, it's just a solid piece, but you'll see hidden detail. So this is the web. Yeah, this is the web of the structure. Okay, and then we have the position of the neutral axis. Right, so you have a position of the neutral axis. It's exactly at the center. Okay, so the neutral axis, and then we have a load coming down at 16 times 10 to the power 3 Newton. Okay, and then now we are going to be rotating about the Y, right? So now the deformation pattern will look like this now. So if you look at the rotation about Y, right? So if you look at the curvature, the rotation, so if you were to focus on this curvature over here, like what I'm drawing that, so you look at this curvature, it's parallel to what? RY. Okay, that's why I say the bending curvature So for this case, the bending curvature is about the y-axis. Okay. So when it's about y-axis, we have to what? Have to employ IYY, second moment of area. Okay. Right. So now the left, so you now this side you have to use IYY, and on the left hand side you have to use IXX. Okay. So buckling will occur either on the at the YZ plane or the XZ plane. Okay. So now I'm going to put down the IZZ value. So IZZ, okay, is given. Okay. So IZZ is equal to 7.752 times 10 to the power minus 6 meter 4, and XX. Hey, wake up, Eugene. So you have IXX. Then you have IYY over here, which is equal to 0.819 times 10 to the power minus 6 meter to the power 4. Now, question for all of you. How weight buckle? Anyone?
Yeah, I by Y is smaller.
Exactly.
Yeah, so you choose that. Yeah.
Yep. So buckling will occur, right, with smaller second moment of what? Area. Right? So we'll buckle with the smaller second moment of area. So i.e. it will buckle on the what? Exact plane. Okay. So now we're going to apply the formula. So with this, we're going to select. Okay, we're going to select. So we're going to select the IYY value, okay, as this have lower resistance to buckling. Okay. So the formula we're going to apply is we're going to calculate a critical load. So the critical load is equal to pi squared over length. Okay, I will call this LE. LE is in fact the length. Okay, multiplied by EI in the YY direction. So LE, which is the equivalent length. I'll explain to you all why equivalent length later. Okay, so this is equivalent length. So this is equal to 6 meters. E, we know that is the Young's modulus is 200 times 10 to the power 9. And we know that we are going to use IYY. Okay, we know that we're going to use IYY, which is equal to 0.819 times 10 to the power minus 6 meter to the power 4. Right? So for this case, we can calculate our critical load. So therefore, the critical load is equal to pi squared divided by the equivalent length, right, multiplied by the Young's modulus, multiplied by IYY is equal to 0.819 times 10 to the power minus 6. Okay. So from here, we calculate that the critical load is equal to 44.906 times 10 to the power 3 Newton. Okay, so that's the